Hi everyone. So today I'll be going over how you can use the WE scripts to set up your simulation. So you can see that there are many files that are needed to start this WE simulation, and basic explanations for each script is listed here. But I'm going to go over these in more detail so that you can use these as a template or reference for your WE simulation. So first, we have the basis states, and this file is a text file that lists all of the starting initial structures. So here we just have two initial states, 0 RST, 1 RST. RST is a specific format for the Amber simulation engine. And here we have the weights or probabilities of each initial starting structure. And in this case, we just set them to be 0.5, 0.5, and they all need to sum up to 1. And here, 0 and 1, they just refer, they're just names for the starting initial structures. And I just listed them as 0 and 1 for convenience. And so where can we find these basis states files like the RST files? For these, they can be found under the B states folder, and you can see 0 RST, 1 RST. And in the west.cfg, the West configuration file, this is one of the main files that are really important for the WESTPA WE simulation. You can see that as we scroll down, here in the data reference section, you can see under basis states, you can see how this specifies that we need to look under the B states and look at the ones with the RST extension. And so how do we pick these initial starting structures in the first place? So most commonly, we have a structure that we would like to simulate. So we go under the regular MD simulation steps, including minimization, heating, equilibration, and then oftentimes we do a short production run in a few nanoseconds. And then from there, we extract some of the initial starting structures. So for instance, this is the 20 nanosecond production run of the original spike protein. And here we plotted the RMSD relative to the starting structure at 0 nanoseconds. This is a 20 nanosecond run. And you can see that the RMSD starts to converge maybe around the 15 nanosecond region, even though it's still oscillating. And so we decided to extract. So here I only showed two initial states just for simplicity purposes, but for the spike protein, we actually extracted 50 starting initial structures from the last 5 nanoseconds of this 20 nanosecond run. So here you can see this is a CPP trash script that's used for Amber simulations, and you can see we're reading the parameter file, we're reading in the trajectory, the 20 nanosecond trajectory, and we're extracting the last we're extracting 50 initial starting structures from the last 5 nanoseconds in evenly spaced intervals. So that's how you often extract and prepare the basis states for your WE simulation. Oftentimes you just want to extract the initial starting structures from when the production run is about to converge. So now that we've gone over B states, basis states, we can look at the config folder. This folder has the needed parameter topology files that are needed to start the simulation. So here we have closed parmtop specific for Amber. And here we have two MD simulation input files. Prod init is used for Amber. And the only difference between this one, prod init, and prod in is just this first line. And that's only because these initial starting structures, for this case, they did not have any velocities included. So this just tells us that we're just going to read the coordinates. And if you look at prod in, you can see that the first line is different. All the rest of the lines are the same. And here it's telling us to read both the velocity and the coordinates. And so similarly, if you're using another MD simulation engine like GROMACS, LAMMPS, etc., you can specify your MD input file that's going to be needed for all these segments and walkers at each iteration. And here we have another PDB file, and that's only because for the spike protein, we needed to get the RMSD relative to this particular PDB. So that's why it's in the config file, because it's needed at every iteration for these segments and walkers. And similarly, let's look at runseg.sh. So this is one of the very important files that is going to be executed for each segment or walker that's going to be run at each iteration. And you can see that we're copying over the parameter topology file from the config folder, as we mentioned before. It's also copying over this analysis.cpp trash, which I'll go over after this. And here we can see that the config prod in, config prod init in, they're being read in. And you can see that this is only read in when we're starting out the WE simulation at the very first step. Whereas this one is going to be used for the subsequent iterations. And so here, this line is the line that executes the segment or walker simulation. So it's reading in the parameter topology file, the MD input file. It's reading in some other files and also outputting some other files as well. That's specific for Amber in this case. And then we execute CPP trash with this analysis.cpp trash. And in this case, this needs to be done in order for us to get the new progress coordinate values and also the auxiliary data values. So after this is executed, all these .dat files are produced. And from there, we can read in the new progress coordinate values. So it's returning to WESTP core return. And rest of these lines are for the auxiliary data that we're keeping track of. And so for these, we should look at west.cfg again. And you can see all the data sets that we're keeping track of. Those are the ones that you just saw in the runseg.sh. Here, this is the progress coordinate, and these are the auxiliary data that we're keeping track of as well. And we specify them again here, which is needed. But this is only needed for the auxiliary variable data, not the progress coordinate. Also, for WESTPA simulations, we can have either one or two progress coordinates. And so in this case, we have two progress coordinates. So that's why the P coord and dim is 2. In the other case, it would just be 1. There are only those two options. And here, the P coord length is the length of the vector that you're going to get from these simulations at each iteration. So in this case, it's 2 because we're only getting the final snapshot from each iteration. So it's 1, but we also have to take into account the parent progress coordinate values or the previous progress coordinate values. So we need to add 1. So 2 would be the shortest progress coordinate length that you would get. If you're taking multiple snapshots at each iteration, then it would be 1 plus that many snapshots that you're extracting. But in this case, we're just extracting one final snapshot. And let's look at analysis.cpp-trash. So this is the file that is used to obtain the progress coordinate values and auxiliary data. And this is specific for Amber again. And here you can see we have to read in the parameter topology file. And this is really important, but we have to read in the parent RST, the previous configuration or structure that we had for this walker and segment. And then we're reading the new segment that's generated from running these simulations. And so from here, all these commands are being used to extract the progress coordinates and auxiliary data. This is specific to the spike protein, and it should be modified for your simulation of interest. And I would also like to note, for the very first step of the WE simulation, the very first iteration, it runs some of these scripts, including get pcord.sh. So this looks very similar to the analysis.cpp-trash that you've seen previously. And I've only copied basically the first few lines that are needed to get the progress coordinate values for these initial structures. And so you can see we're reading in the parameter topology file, we're reading in the initial starting structures and trying to get, in this case, the RMSD and the center of mass distance. And here, init.sh, here this is sourcing the environmental sh to set up the right environment for the simulation. And then it runs winit to initialize the WE simulation. And here, there aren't really any parts that you need to modify. The only part that you might need to modify is uncomment this if you're running a steady state WE simulation. But if you're running a regular equilibrium WE simulation, then you should comment this out and you should only have the B state args. And it's really important to run this when you're initializing your very first WE simulation, but when you're restarting your existing WE simulation, you should not run this. Otherwise, this will delete all of the data that you've gathered so far. So it's really important to not run this afterward. So essentially, for your WE simulation, you should modify this part to extract the progress coordinate values of interest. You should also modify analysis.cpp_traj to modify the progress coordinates of interest. And also, if you're keeping track of auxiliary data, if not, then you don't need to worry about it. And of course, you also need to modify your basis states and B states config accordingly. So now here, I'll go over the rest of the scripts. Environment.sh, you would only need to modify the first few lines. So here, I'm sourcing my profile and also loading all the modules that are necessary for the particular supercomputer that I was using to launch the WE simulation. So this part would need to be modified. And here I set up my WESTPA environment with Anaconda, and I named it as WESTPA, so I need to conda activate WESTPA. This part, well, probably this part needs to be modified to the Python path that you're going to use. And the rest, oh, here, you would also need to modify your local node directory, which is just my Scratch directory in this case, where I ran the WE simulations. But otherwise, you don't really need to modify the rest of the parts. Here, these are specific to Amber. So in this case, you would export the MD simulation that you're using so that the simulation has access to these programs. But otherwise, these ones can just be left it as you can just leave them as is. And here, node sh, this one you probably don't need to modify as well. This is pretty much all set. One thing to note that this is for Slurm, so if you're using something else like PBS, it might need to be modified a little bit, but otherwise it should mostly be the same. And here, post_iter.sh, this is run after the iteration is about to end, when the simulations have already finished. So this is usually run to tar the seg logs and the traj segs so that we save space. In this case, we actually commented out tarring the traj segs. And this is because if we want to make a movie out of these WE simulations, that is, we're concatenating all these iterations to make a movie, then we don't want to tar them because untarring them would be computationally costly. So we commented this part out, and I suggest you to do the same if you're going to be generating movies from your simulations. And runsec, we already went over, but just wanted to make sure. So essentially, you would modify this part so that it copies over the files that you need for your simulation. Probably need to modify these as well, or at least the content. You can leave the name the same, but you should probably change the content according to your simulation. And these parts as well. And here, you can notice that I commented out this line. And you can modify this line if you just have one progress coordinate. Otherwise, you can modify this line, which takes in two progress coordinates. And these are for auxiliary variables, so that's up to you. In our case, we just wanted to keep track of all these variables like the other RMSDs and some salt bridge and hydrogen bonds while we're running the simulation. So that's why we have these auxiliary data. and run WESH. This is the main script that runs the WE. So oftentimes you would just submit this to your supercomputer that you're using to run your WE simulation. So here, this is specific for Slurm. So you would need to modify it if you're using PBS or something else. And so this part is very similar to the environment.sh. So you would modify this part accordingly. And the other parts are pretty much similar. I mean, you can just keep them as is. Here, you should set the number of GPUs per node according to your supercomputer configuration here. Our nodes that we were using had 4 GPUs per node, and these simulations use GPUs to run the simulations because we had so many atoms, so the GPU run simulation would be the fastest. And these parts are the same. And here, since we had 4 GPUs per node, and they're all numbered 0 to 3, so we had this line, but you might need to modify or delete this line. And here, so we're essentially SSHing onto each node that's listed in the node file list that's generated from here. And we're running these simulations simultaneously across all these nodes that we have. So since we're running 1 simulation per GPU, that's why we have n number of workers to be set to be 4, since we have 4 GPUs per node. So we want to run 4 simulations per node. But most of these parts, you can keep them as is and modify accordingly, especially just the top part. And finally, let's look at west.cfg. So here, we only need to modify a few things here as well. Well, I guess more than a few things. We need to modify several things, but not everything. So here, this basically sets the number of segments or walkers per bin. And here we set it to be 8. I think 8 is a pretty good number. You can increase it or decrease it according to your system. And here, we're using the minimal adaptive binning scheme. So we're using the MAB in mapper, and we have 15 bins for each progress coordinate. And these are the boundaries. And so we had to set these accordingly. And I think Anthony has a more detailed video about the MAB binning scheme. So I would encourage you to check that out on YouTube and read the appropriate papers and find the tutorials for the MAB. But this is what we set up with because in this case, we had the RBD center of mass distance from like 50 to 100 angstroms. And we just wanted to have 15 bins here. So that's why we have this. We're placing this MAB binning mapper between 50 and 100. So that's why we have 51. And for the RMSD, we could just have it at any value. So we just set our boundary to be 0 to infinity, and between 0 and infinity, we just pick 0.1. So this basically specifies where to place these like 15 by 15 bins. And so if you look at 51, that's between 50 and 100. So it would be along here. And 0.1 is between 0 and infinity. So it would be just placed along here. And here, we also set the max total number of iterations. It's also important to set the max runtime wall clock. In our case, 48 hours was the maximum, so we set it to be a bit shorter so that it would finish up the simulation cleanly, even if it didn't run all 4,000 iterations. And most of it, these parts, they can just be left as is. We already went over this, the progress coordinate and the auxiliary variable data. These parts are mostly already been set by default. I would just recommend you to just make sure that your initial starting states are in this directory with this format. I mean, this is only specific for Amber, so if it ends in something else, I would replace this with that extension. And here, these are the progress coordinates again. And these were already there by default. I wouldn't really change much. And this part is just for the analysis, and these can be modified post simulation. And I will go over this part in another video. And I wouldn't worry about this for now. We can modify it after the simulation has ended. And so with that, I hope that this video was helpful in allowing you to use these WE scripts to set up your WE simulation. If you have any questions, let me know. And I'll see you in the next video that will go over the analysis scripts. Bye.